much, Tim. That was really an excellent talk.
Okay, thank you.
Okay. All right, so our next speaker is Tobin Munsat from the University of Colorado, and he is going to give us an overview of recent science results from the CCLDAS Dust Accelerator. He's going to tell you all about that. This is part of Mihai Harani's team, part of the NASA Lunar Science Institute, and we look forward to having this talk. So welcome, Tobin. Please take it away.
Thank you. Let me just start this webcam and get going. Like you mentioned, I want to give an overview or kind of a sampler of what we've been up to at the Dust Accelerator at the University of Colorado, which is, as you said, under the umbrella of the NLSI. The first thing I want to point out is that I'm giving this talk on behalf of a large team of people, and I'm presenting work which was done by all the people on this long list, which includes people at all different levels. So let me start by just saying that we have a Dust Accelerator, and I want to just start with a few slides that tell about the facility to cover the technical aspects. You can see a website down here at the bottom. You can tune in at any time to see what we're up to at dustcam.colorado.edu. And the accelerator itself is written up in all of its detail in a paper, which I've listed here at the bottom just underneath the photograph, which is first authored by my graduate student, Anthony Hsu. To go over the quick technical description of what the accelerator does, this is a linear electrostatic accelerator. We charge up particles and then launch them down the beamline. We achieve velocities which are in the neighborhood of tens of kilometers per second. We actively select particle by particle which charges and which velocities we want to have reach the target. We can accelerate any kind of material as long as it can conduct so that we can have efficient charging. So our workhorse material is iron, but we also can do aluminum or silver or even non-conducting materials if they are coated with a conducting surface or coating. The particle sizes that we're talking about are on the order of a micron. The next slide shows a distribution of the particles that are launched out. So during a run, we down-select the population to any subset of this distribution based on the charge and the speed of each particle. And if you look at the lower right side of this distribution, you'll notice that the fastest particles, the speed is on the x-axis, are also the lightest. The mass is on the y-axis. And these are also the lowest charged particles. And to detect these and to use these, we're pushing towards the noise floor of the triggering system. So in order to get around this, we've developed a real-time digital filtering system, which is encoded onto an FPGA board. And so just to give a very quick summary, we can take a very weak raw signal, which is the detector signal from a particle going through one of the detectors in the beamline, which is embedded in noise, which if you look at the top plot, that's the blue, very messy looking plot. That's a weak square signal embedded in a lot of noise. And we can use this digital filtering to turn it into a very clear triggerable signal, which is the black V-shaped curve on the plot. Now, if you want all the details of how this is done, you can watch for a paper which is coming out hopefully soon by another one of my graduate students, Evan Thomas. So that'll be published, well, let's just say eventually. Now, there's a few implications of this. Obviously, it helps us to use particles, fast particles, that we couldn't access otherwise. And also helps us to customize the selection criteria for in fancier ways because we can program them right onto the chip. And also this technology is transferable to other signal processing tasks. And it's all implemented through a LabVIEW interface. Like I said, this work was done by a graduate student, not by a senior engineer. So with the performance enhancements to the device, to the accelerator, that allows us to achieve what we're really after, which are the primary science experiments. So the classes of experiments that we're after are looking at impact products like secondary ejecta, neutral gas, plasma products, looking at light flashes from impacts, primary and secondary light flashes. We use mini ion gauges to look at neutral production. We look at cratering studies. And finally, we do instrument development and, importantly, testing of flight instruments. So let's start. This is where the sort of sampler of the experiments begins. Let's start by talking about a temperature measurement of plasma, which is produced by the impacts. This work was done by Andrew Collette, who's a member of our local team. You can see the experimental setup on the right, which uses photomultiplier tubes with narrow band interference filters to piece together a spectrum from which we can get a black body temperature. And what was found, just in brief, is that the temperatures are in the range of 2,500 to 5,000 degrees Kelvin. That increases with increasing impact velocity. And the temperature evolution can actually be time resolved over the lifetime of the flash, which is just about 20 microseconds. And if you look at the bottom of the slide there, you can see the publication, which was published by Andrew, which is in print this year. Andrew has more recently done a series of experiments to measure the neutral gas production from impacts, which is actually quite a tricky measurement to make because the pressures are so low. So for the plots in this slide, dust particles are shot right into a gauge. On the left, you can see the impact signals with the filament on and off, respectively, which helps us to discern real impacts from artifacts. On the right, you can see the total ion charge collected from the gauge with the filament on and off, which are the different colors, over a wide range of particle masses from which response curves can be derived. And again, these are tiny, tiny little signals. The pressure rise in the ion gauge body is just a few times 10 to the minus 10 torr. And there's actually a lot of complexity to these experiments and these results, and I just wanted to give you an idea of what was going on. But tomorrow at 10:15 Pacific time, Andrew will be giving a talk on these experiments and these results at 10:15. So next, we've also done some experiments looking at the impact flash produced by ejecta from hypervelocity impacts. These are the ejecta that may be responsible for rings and dusty atmospheres of moons, for example. And we need to develop a clear understanding of the ejecta parameters, like velocities and masses and angular distributions, to figure out the ejecta yield. So the experimental setup is shown in these images. The primary projectile from the accelerator comes in and hits the target. That's the red arrow in the diagram. It creates an impact flash, and then the ejecta come out and hit the quartz face of the PMT and make a second flash. Here are just a sampler of some plots. This is an example of what the data looks like when you get a primary flash and a single or a series of impact flashes, which can be separated out so that you can resolve the secondaries using time-of-flight techniques. This work was spearheaded by Keith Drake, who has a poster in this conference, which you can check out. Now, a whole other class of studies has to do with the craters that are produced by impacts. So, like as one example, cratering studies are critical for understanding the response of this material PVDF, which can be used as a dust detector. So PVDF is a dielectric that has a permanent polarization, and when it's used as a detector, the impact craters will remove some material, leading to a change in the surface charge, and that charge can be measured with a charge-sensitive amplifier. And the calibration of this is critical, so we need to turn the dust characteristics, which we know from the accelerator, into the crater characteristics, which we can measure using these techniques, and then transfer them to the detector signals, which we also measure. Most of the 3D crater analysis is done by stereoscopic reconstruction using electron microscope images. So here on the right, you can see a raw microscope image of a crater that's just a couple of microns across. And you can see that there's a tremendous amount of detail in there, which we can resolve and use. And on the left, you can see the 3D depth profile reconstruction, which is also verified intermittently on a handful of craters by actually cutting down through the depth profile using a focused ion beam. This work is written up in a paper by Anthony Hsu, graduate student, that'll be coming out in print soon. And Anthony also has a poster on this work in this conference. Now, changing gears again very quickly, we've done a series of experiments using a linear time-of-flight spectrometer, which we use to look at the ion production or the total charge yield due to the impacts as one measurement. So here's the instrument just sitting in the target chamber. We can move that around to look at different impact angles. There are a lot of different results from this series of studies, but I just want to show a couple of plots as an example of the kind of thing that we're doing. So on the left, you can see plotted the impact charge is plotted against the impact speed. And as we transition from the production of weak shocks during the impact to stronger shocks at higher velocity, we change from primarily surface ionization to deeper volumetric ionization. And the charge production takes a clear jump upward, so that the different regions are shown with the different colors in the left-hand plot. Now, the data points can be put into a scaling law with charge versus mass and velocity to different exponents using fits. And these are shown on the right. And you can see that the scaling is different on different sides of this transition between surface and volumetric ionization. This work was done by Anna Macher as part of our international partnership with the Heidelberg team. And I've listed at the bottom of the slide the paper which she writes up all these results. The plots that I'm showing are just one of many results that are done from this series of studies.
You have
now,
2 minutes.
A practical consideration of this charge production beyond just the basic science is the pickup signals on spacecraft instruments. So, for example, on the stereo spacecraft, they see signals on their antennas from what they think are dust impacts. So we've done a series of experiments on the Accelerator to look at this effect or this phenomena in detail. This work was done by Zoltan Sternovsky and Keith Drake, who are on our local team here. So the image on the left just shows a simple schematic of one of the first experiments that they did, where an antenna with similar electronics to stereo was put into the dust beam, and the impact charge was recorded and detected. And the plot at the bottom shows one of these unambiguous signals from a dust impact, showing that it really does produce charge. The image on the right shows a more recent version of a target setup to measure the characteristics of charge production in general from impacts onto spacecraft surfaces. This is basically my last slide. I just want to mention, again, as you saw a couple of slides ago, the CCLDAS dust instrument on LADI was calibrated in this accelerator. And though the main instrument is going to be launched in a couple of months, we all know that it sometimes, occasionally, becomes important, even after the fact, even when the instrument is in flight, to have the engineering model handy with a calibrated source of hypervelocity dust. And so that is still available here. So I'll leave you with an image of LDAX, which we're all excited about, and I can take any questions now.
Great, thank you so much. Okay, you have one question already in. Tobin, can we compare the kinetic energy of the particles with the energy released after the impact? Are they similar in magnitude? Which is bigger?
Well, the energetics is a complicated question, because energy goes into a lot of things. It goes into plasma production, it goes into light production, it goes into the chemical release of neutral, and it goes into perhaps what you're asking about, which is the kinetic energy of the ejecta. So what we have found so far is that the kinetic energy of the ejecta is some fraction, not larger than the kinetic energy of the impinging main particle. But we are not yet at the point where we can make a sort of a blanket statement about where all the energy is partitioned between these multiple effects. That's kind of our pie-in-the-sky goal for a lot of these accelerator experimental campaigns, and we're just not there yet to put together all of the results. And I think there's simply a lot yet to be done, and we'll continue to try to go for that. But that's one of the most important questions that we're trying to get at.
Okay, great. And what's next for the accelerator? Do you have a new campaign planned?
Well, we have a number of new things in mind. I mean, sort of, adding on to what I just said to the previous question, we have a lot yet to be done with these sorts of scaling studies that we're just scratching the surface of, and there's a lot of sort of parameter space to explore. But in addition, we have a couple of major upgrades or enhanced capabilities to the facility in mind. One is to enhance the thermal control at the target end. So we can bring instruments up and down in temperature, and also have the ability to send particles into frozen targets. And so obviously out there in the solar system, there's a lot of locations where we can duplicate frozen or icy targets. And even just saying icy targets leaves open a lot of possibilities for ways that targets can be icy or can be frozen. So that's just a whole new class of targets that we're after. The other sort of avenue that we're trying to pursue next is gas targets. So if you think about, for example, the upper atmosphere of the Earth, when micrometeorites come into the Earth's atmosphere, they ablate, they emit light, they turn into gas, they create plasma. And so we should be able to mimic that phenomenon in our accelerator, obviously not using a kilometer-long trail, but actually using a higher pressure gas in a very controlled way to make a smaller ablation trail, but measure the charge production, measure the light production, and get a handle on this phenomena, which even after all these years is still not very completely understood. There's a sort of a wide error bar or unknown bar on what these plasma production and light production are. And this is actually very important for a lot of things. It's important for things as basic as interpreting, as Mihai mentioned briefly in his talk, interpreting how much dust is coming into the atmosphere. They look at light trails and plasma production to try to interpret how much dust is coming into the sky, using the whole sky as a giant dust detector. But those are quite uncalibrated measurements, and we have a chance in our dust accelerator to calibrate those in a very controlled way. So we're excited about that.
Sounds wonderful. Great. Thank you so much.